Hi, this is Mingyu Wu from Shanghai Jiaotong University, and I am very honored to present our work in the first virtual VE conference. Our work is about building an efficient GCPersist lazy processing framework for resilient Java applications on non-volatile memory. This is a joint work from Shanghai Jiaotong University and the National University of Defense Technology. As we know, non-volatile memory has many advantages against other traditional devices. For example, it has better traceability, fast access speed, durability, capacity, and power efficiency. And with the advance of technology like 3DX Point and devices like OptDC persistent memory, NVM is now available at the market. Prior systems have already provided native support for NVM on high-level languages like Java. In this work, we will mainly focus on the native support for Java on NVM, because they allow storing objects to both DRAM and NVM, which enables high performance and ease of management. The representative systems of those native support are Espresso and AutoPersist, which have been published in private conferences. Those private systems share a similar eager persistence model. For Espresso, it requires users to add flash for eager persistency. For example, to persist array-related data, the applications need to write array.flash, which will be translated into sfns instructions and cache line read back instructions. For AutoPersist, although the user do not need to add those flash instructions, the JVM will instrument necessary instructions in the background. Although the eager persistence model can achieve timely persistency and it is suitable for fine-grained updates, it also introduces large persistent overhead because they have too many CLWB and sfns instructions. Resilient applications are a kind of applications which have fault-tolerance mechanisms such as replication and recomputation. Those applications may fail due to many reasons. For example, the hardware failures, software bugs, and out-of-memory errors due to memory bloat. Although they have implemented their own fault-tolerance mechanism, the mechanism may not be efficient enough. For example, the recomputation may introduce large CPU overhead. In this work, we use Spark as an example. Spark is a unified big data analytics engine. The core data structure of Spark is RDD, which actually stores data arrays. Each RDD will store how it is computed by other RDDs. It is called lineage in Spark. For example, this is a chain organized by 3 RDDs. The RDD2's lineage is RDD1 and a flat map, because RDD2's data is computed from data in RDD1 and the flat map operator. Similarly, the RDD1's lineage is RDD0 and the map operator. When a crash happens, the data will be recomputed according to lineage. For example, if the data in RDD2 is lost, it will be recomputed from data in RDD1 and the flat map operator. If the data in RDD1 is also lost, we will recompute it from RDD2, RDD0, and the map operator. In the worst case, all data in all RDDs are lost. We will start from the beginning and reload the file and recompute the data in all RDDs. Spark already provides a cache API to keep RDDs inside DRAM for fast access. However, the cache API is not resilient to crashes. When a crash happens, the cache data will still be lost. So, we have provided a strawman design which moved the cache RDDs from DRAM to NVM. We have implemented the design on Espresso. If a crash really happens, since the data in RDD1 is in NVM, it will still be available during recovery. So, we will directly compute the data in RDD2 by retrieving the data in RDD1 and using the flat map operator. In this way, we can reduce the recomputation during recovery. Here is the benefit of the NVM cache. We have conducted a recovery test on Spark application logistic regression. We send CKIL signals to simulate crashes. and we collect data from the logs in Spark. We have simulated two different kinds of failures. The DRAM is the hardware failure, where we clear the file cache. DRAM plus page cache is simulating software failure, where we avoid cleaning the page cache. As we can see, compared with the DRAM configuration, we can reach 7.54 times improvement in task execution. And compared with the DRAM plus page cache configuration, we can reach 2.44 times improvement in task execution, which shows the benefit of the NVM cache. However, NVM cache, the cache also introduces large overhead during normal execution. If we run the logistic regression for 100 iterations, the execution time is actually 29% longer. We have broken down the first 10 iterations. For the first one, we can see that the execution time is nearly doubled. This is because in the first iteration, the RDD needs to be persisted in NVM, so the overhead of data persistency is very large. For later iterations, we can see that the performance is still 21% slower. It's because there is a performance gap between the DRAM and the real NVM device. Our alternative design is lazy persistency, which means that the persistency can be deferred to the future. Compared with the eager persistency, lazy persistency uses less advanced instructions and CLWB instructions, so they can reach better performance. Prior work also proposes lazy persistent models. However, they are mainly designed for C or C++ code, and they have limited usage scenarios. As we know, there are many uses for transactions. We have analyzed the GC algorithms in OpenJDK and find that there are many copy-based algorithms. For example, the PSGC, the G1GC, and other collectors all uses copy-based algorithms. They will all start from root objects, which are stack variables and some global metadata. And they will copy all reachable objects from the roots to their destination addresses. So our idea is that we can persist those objects during GC. When objects are copied to DRAM, we can integrate with the copy-based algorithms to copy objects also into NVM to finish persistency. In this way, we can leverage the efficiency of garbage collection to reduce the persistence overhead. So here comes our solution. It is called GCPersist. It contains two parts. The first part is a GC-assisted lazy persisting model, which integrates with GC to persist data objects, and it can reduce the persistence overhead. The second part is snapshot persistency. In this part, the objects in NVM will only serve as a snapshot, and it will only be used during crash. In this way, we can avoid frequently accessing the NVM and filling the gap between NVM and DRAM. We will first introduce the GC-assisted lazy persisting model. It mainly contains three important components. The first one is persistent data identification, which is achieved by the SafeRoot API. The second part is the asynchronous reachability-based persistency, which is mainly achieved by GC. The third part is post-crash inspection, which is achieved by check-heap API. We will introduce them one by one in the later slides. The first part is persistent data identification. We mainly use the SafeRoot API, which can mark objects as persistent roots. For example, we can mark this object with the SafeRoot API. Later, JVM will know that all objects reachable from the blue objects should be copied to NVM. The SIGOPS API is actually very easy to use. With this API, the user only needs to mark the roots instead of mark all the objects. The second part is asynchronous reachability-based persistency. As we mentioned before, the GC algorithm will start from the GC roots to mark all reachable objects. In our design, we will add persistent roots into the root sets. During marking, will mark objects according to reachability with two different marks. If an object is reachable from volatile root, it will be marked as volatile. If an object is reachable from the persistent root, it will be marked as persistent. If an object is reachable from both volatile root and persistent root, such as this object, it will be marked as persistent. After marking, we will copy objects according to their marks. If an object is marked as persistent, it will be copied to NVM. If an object is marked as volatile, it will be copied to DRAM. So after copying, the heap image will be like that. In this way, we will achieve persistency during GC. The third part is post-crash inspection. In this part, we propose a check heap API. Since after crash, all data in DRAM will be lost, and only data in NVM is available. So we provide check heap API to inspect if the heap is valid. The check heap will start from the persistent root and traverse the objects to see if there is no references can escape out of NVM. In this example, all objects are inside the NVM, and all references is inside the NVM, so it is a valid heap state. And in this case, this reference is out of NVM, so it is an invalid case. In this case, the check heap will directly return false, so application like Spark can know that the data in NVM is actually invalid and cannot be used during recovery, so they can use their own fault tolerance mechanisms such as replication and recomputation. The second part of our design is the snapshot persistency. It is mainly used to fill the performance gap between the DRAM and the real NVM device. The key design of the snapshot persistency is to split objects during GC. As we can see, if an object is referenced by both volatile and persistent roots, such as this object, we will split it into two copies. And during copying, we will move one copy into NVM and move another copy into DRAM. And the result is that there will be no inter-device references. That is to say, there will be no references from NVM to DRAM, and there will be no reference from DRAM to NVM. In this way, we can move all objects in DRAM to the foreground, and move all objects in NVM to the background. In this way, all objects in DRAM can serve as normal access, and all objects in NVM will be hidden in background and only be used during recovery. In this way, we can avoid access to NVM and avoid the performance penalty in accessing NVM. GCPersist is implemented on PSGC, the default garbage collector in OpenJDK 8. And we have provided another optimizations. For example, we have discussed another persistent mode called single copy persistency. We have also discussed the persistent points. We provided some optimizations on read-mostly datasets. For more details, please refer to our paper. For the evaluation, we use the real Optane DC PM devices for evaluation. And for the software, we use OpenJDK 8U and Spark 2.1.0. We use 4 built-in applications in Spark for evaluation, and for the baseline, it contains 3 parts: Espresso and AutoPersist. For AutoPersist, since it is not implemented on OpenJDK, so we have implemented a simplified implementation on our own in the OpenJDK platform. The third part is the vanilla Spark, which is an unmodified Spark without NVM cache. Okay, for the recovery time, as we can see, the GCPersist can achieve recovery improvement for all applications compared with the vanilla Spark. The improvement is from 9% in transitive closure to 3.26% in logistic regression. And if we directly compare the task execution time, which is mixed here, we can achieve up to 8.50 times improvement for the logistic regression application. For the PageRank application and the transitive closure application, the improvement is less. It's because they mainly use smaller datasets. And for the normal execution time part, compared with AutoPersist Star and the Espresso, GCPersist actually can achieve moderate overhead among all applications. The overhead ranges from 1% to 6%. And for the K-means application, we actually reach a slight improvement compared with the vanilla Spark. Compared with our GCPersist, private eager persistent model actually introduces large overhead. For example, for AutoPersist Star, they can achieve up to 46% overhead. Okay, to conclude, there are actually two issues hinder residing applications from using NVM. The first one is that they mainly use the eager persistent model, which will eagerly flushing objects into NVM and induce large persistent overhead. And the second is that the performance gap between DRAM and the real NVM device. We present GCPersist, which integrates persistency with the garbage collection. It contains a GCL60 lazy persistent model, which can reduce the persistent overhead. It also uses snapshot persistency, which can avoid accessing NVM unless a crash happens. The results show that we can achieve significant improvement during recovery with moderate overhead. Thanks for listening, and I'm ready to take questions.